So let's look at another derivation of the Laplace transform. Now, if you can remember, whenever we did the original derivation of the Fourier transform, we thought about the dot product between two vectors, so the dot product a dot b would be a1 b1 a2 b2 all the way up to an bn. Now, if we were to then write this as a general inner product, now we've also seen this here, let's take it as for example of f and k, that can be written as the integral from minus infinity to infinity over function f of t times k of t by dt, and that would be our inner product. Now, we mentioned that whenever we were deriving the Fourier series, so maybe if you're unsure of it, you can always go back and have a little look. Now, when we did the Fourier transform was in this form here, the integral from minus infinity to infinity of f of t e to the minus I omega t by dt. So really what we were saying was, we're taking the function f of t and we're decomposing it onto an orthonormal basis, and the orthonormal basis is given by that e to the minus I omega t. So let's say, for instance, for the moment we just replace this minus I omega with a value of s. So we would have this integral from minus infinity to infinity of f of t e to minus st by dt. Now, let's remember that I'm just doing this in order to get this into a kind of general form for us to deal with. So if we were to note this little section here, the little function e to the minus st, so we would have the k of t would be the e to the minus st in this example. So we'd have a function k of s and t, which would be equal to e to the minus st. So in this instance here, the variable is going to be time, and the value of s is going to be a parameter. So really what we're saying is that we can pick a value for s, and then we can let t range between plus and minus infinity. We could then take another value for s, and again t could range between plus and minus infinity. And for each value of s that we take, we'll let t range, and then we can look and see what the output is of this integral. Now this little thing here, written in this form, k of st, is something in mathematics sometimes called a kernel. So the point that we're going to be making here is that if we can choose this k of s and t, so this is our orthonormal or orthogonal basis, then we can choose it in order to have particular attributes. Now that's the whole point of doing integral transforms, that you can choose particular values for the parts of the integral that will give the transform a particular attribute. Now the attributes that we're going to be looking for are that we can make differentiation in some way look like multiplication. So that's what we're going to be doing on the next screen, the next slide. But just one thing to note before we go on with this is that we want this integral here to converge. So really what we want to make sure is that the limit as t tends to infinity of all of this would have to tend towards 0 in order to ensure that this integral from minus infinity to infinity is going to converge. So let's go ahead and see how we can pick the correct value of this kernel k s of t in the next slide. So we want to choose the kernel k of st in order to give us a particular attribute. Now the attribute you're looking for is that we want to ensure that when we differentiate a function in time, it's equivalent to multiplication of a function in the other s domain. So what kernel is going to give us that? Well, we can write this down more generally. We can say we're going to do some sort of transform of a derivative of the function, and that should be equivalent to the transform of the original underived function times a factor of s. So what kernel do we need in order to make this true? Now first of all, we're going to note that we're wanting the whole thing to be causal, so we'll change the integration limits from 0 to infinity. So we're just going to rewrite this up here in terms of the transform that we have. Now the transform we have is our dot product, okay, so we're going to rewrite the left and right hand side. So we're going to have the integral from 0 to infinity of our transform, which is going to be our k of st times our d by dt of f all by dt, and we want that to equal the right hand side, which is the transform again, which is going to be the integral from 0 to infinity of a factor of s times the original t of s, which is just going to be our k s of t times f by dt. Now you might not be able to see where we can go with this, but one route that we can take is that if we could cancel out the values of f here and the value of f here, then you would see you would have an integral from 0 to infinity of k of st and an integral from 0 to infinity of k of st here, and we could cancel this whole thing out. But in order to do that, we have to get f out of this differential. Now we can do that using integration by parts, because integration by parts really in this instance here will allow you to take f out of this, and it would bring the k to the st inside it. Now I haven't gone over integration by parts here really in this series, but I will do a write up at the back of the notes if you're interested in the appendix. So really integration by parts is similar to the product rule for differentiation. That's a kind of product rule for integration. So if we had two functions, we call them u dv, and we were integrating them, that would be equivalent to saying u times v minus the integral of v du. So in this instance here we'll make our u equal our k of st, and we'll make our dv equal d by dt of our function f. So now we can see that our value here of u times v, well, u is just the k of st, so that's the k of st here, times the value of v. Now v, this here is our dv, so in order to get back to v, we would have to integrate this side. So in order to integrate this side, we'd have to integrate that, so that would just give us back our f of t. So we'll simply have here our k of st times f of t, and that will be from 0 to infinity. Now the second part is minus, and it's minus the integral of v du. So the v is here, okay, but that's actually dv, okay. We don't want dv, we're actually wanting v. So again, we just integrate that to get v, and we're left with the function of time. So that's that function of time here. And we've also got our du. Now du, to order to du, we have to differentiate this here. We're differentiating with respect to t, but of course it's a function of two variables, okay, so we're holding s constant and varying t, so we've got to use partial differentiation. So it's got to be partial by partial t over function k of st. So leaving this bit out here for the moment, what we're going to be left with is this part here, which has just been rewritten here, and we want that to equal what we have above here, which is our integral from 0 to infinity of s k of st f of t by dt. Now you can see that this line here, this equality, we've got what we want. We've been able to take the f of t, that's f of t, out from inside this differentiation and place a k of st inside it. So now the k of st is getting differentiated and the f of t is outside. So that allows us then to cancel out the f of t's here and cancel out the whole of the integration, and we're simply going to be left with this minus partial by partial t of k of st is going to equal s times k of st. Now I've just taken the negative over to the other side and rewritten that here. So now we just have this simple little differential equation, which is partial by partial t of k of st equals minus s k of st. Now the only solution to that partial differential equation is that k of st equals e to the minus st, and you can see that quite simply. If you go and differentiate that e to the minus st, you end up with s times e to the minus st. Okay, so that means that the kernel that we need in order to make the differentiation equivalent to multiplication is the the function e to the minus st. So therefore we can say that our f of s is going to equal the integral from 0 to infinity of f of t e to the minus st by dt. So this here is the derivation of our Laplace transform. So finally we'll look at this little section here, which is the initial condition. Now we have this k of st times f of t, so we said here that we had to ensure that the original integral had to converge, so we say the limit as t tends to infinity of our k of st f of t would have to equal 0. Okay, so that means that this thing here is going to equal 0 whenever t tends to off to infinity, and then we're going to have it minus the value of this whenever we put the value of 0 in for t. So it's going to be minus, and if we put the 0 in for t, you get f of 0 and k of s0. Now the k of s0, well, it's just e to the minus st. So whenever whenever t is 0, that's just going to be a value of 1. So it's just going to be 1 times f of 0, which is just f of 0. So finally, we could say that our Laplace transform pair for the differentiation would be when we differentiate a function with respect to in the time domain, it's equivalent to multiplying the Laplace transform of the original function times your value of s minus the initial condition f of 0. So quite a lot of maths in that, and it maybe take a wee bit of time to work through it, and I'm kind of used to it because you come across integration by parts all the time, and if there's one part of a calculus you really want to understand the use of and the usages of, that would be integration by parts. Now we will go over what happens whenever we differentiate a function in time domain, and when we take the Laplace transform. We will go through another derivation of this, and it'll be a graphical derivation. Okay, so this really is just an added extra in this video, and the main point is the derivation of the Laplace transform given here. So thank you for listening, and goodbye.